Welcome back, everybody. In this series about neural networks, we've covered a lot. We started out with the introduction, talking about those nodes and the arrows pointing at different nodes and what that all means. The next part, we looked at a neural network. We went ahead and coded this thing up, and then we looked at a little bit of normalization in the last part. So one of the things that you can notice here is that we're just building a simple linear model. This is, again, the simplest neural network possible so we can understand what's happening. But what should we do when we want to go to something a little bit more complicated? To make all those fancy like image recognition neural networks that we've seen that captures things like I can identify a cat in a picture, or given any set of handwritten digits. This is sort of the hello world example of machine learning, or deep learning rather, is where you take those handwritten digits and then you classify them. So in order to get to something like that, you can't just use a linear model, and you probably shouldn't be coding everything by hand. So before I dive into the techniques to get around that and the package that we're going to be talking about to do this simple example, I think it's worth just reviewing what we did so far. So let me go ahead and run this thing that we had going on before. So if you recall, we had this simple model that was trying to capture temperature on the x-axis and relative humidity on the y-axis, and then you saw this black line sort of converged onto the realistic slope. And the steps to do that was just to simply load the data, normalize the data. That's what this normalization part is here. Normalize the data, meaning give it a mean of 0 and a standard deviation of 1. So sort of squish the data down. And then define some initial guesses of what the slope and intercept are. So this is something that you just pick. And then the way that what happens down below when you iterate over the epochs is that you're slowly converging on what the correct slope and intercept should be. Fantastic. All right. Now you can imagine, of course, this is going to get messy. And the reason why it gets messy is we had to do this update rule down at the bottom. So we take some initial guess here, y guess, where we just do this mx plus b situation where we're doing a linear system. Now imagine if you want to add some nonlinearity. So we're talking about linear system. Okay, if we wanted to add a nonlinearity, then what we do is you wrap a function around here. Let's say some sigmoid function, something to add some complexity and nonlinearity. And this is also just one node. So this is one of those circles and arrows images. This is one node. If we wanted to add another node, we'd have to have something in between here. We'd have to have something called like a hidden layer. You can imagine adding this in here. So the hidden layer, and that's going to be some sigmoid. And notice I didn't define what the sigmoid function is, so don't worry about that just yet. That's another, but just know that it's some kind of non-linear operation. So it takes this equation for a line, and allows it to have some kind of curve to it. So that way it can fit something fancier than just a line. And so we can put in our inputs x plus intercept guess. So that's one intercept guess. And then what you'd have down here is, since we want the output to be linear, we would have this be hidden. And this is a different intercept. We'll call it intercept for the h, the hidden layer, and another slope. So now instead of having two parameters, the slope, a single slope, and a single intercept, when you start adding layers or nodes, those circles, to your neural network, what you're going to end up having is these hidden layers that then have to have their own set of slopes and intercepts. So here we'll have 4 parameters. We'll have 2 nodes, a hidden layer, the output layer, or to get to the output layer, and what you have is a slope and an intercept for the hidden layer, and then another one for the output layer. So you can imagine, as you keep stacking layers on top of each other, as things get deeper and we start to build a deep neural network instead of just a basic linear model in this case, things can get really complicated. And aside from the number of parameters that you have to be updating, you would also have to keep track of this backpropagation step, this update rule. So how would you define this change in error with respect to slope? Instead of just doing the partial derivative with respect to slope, you'd have to do that for not just a single layer, you'd have to do it for multiple layers. So here you would have to do it for this sigmoid as well, and this can get quite messy. We don't want to have to do that ourselves. So there, of course, have been packages built to make your life a lot easier so you don't have to build these kind of networks from scratch like this. One such library, one such package is called Keras. Yay! All right, let's take a look at Keras because it is awesome and simple. All right, so Keras spelled like this, It's actually not the package that does the actual model training itself. What it is, it's a high-level wrapper. And as they say on the front page of their website here, you can see this. They are essentially just wrapping up other libraries, other Python and low-level libraries that will handle doing things like backpropagation, meaning this update, this change of your slope with respect to your error. And I'm sorry, the other way around, error with respect to slope. And so what they'll do is they'll wrap that package for you and make it a lot less verbose. That way you don't have to write these loops yourself, as you can see in here. So we're going to do this simple model with Keras. That way we can understand what's happening. And then we're going to start playing around really slowly to add a few layers. That way we get a good feel for what's happening, and we can start building a little bit more complex models. And the real, I really need to focus on this because this is very important. Make sure that after you get an idea for what Keras can do, you go and play around with it yourself. And I think that's very important. That helped me a ton when I was working and trying to learn this stuff. Just go grab a data set like I've done here, a real data set, a real messy data set. Come up with some objective. Even if it's something simple like, I want to see if I could overfit. So this is something that I haven't talked about here, but this is something that deep learning models are prone to do, deep neural networks are prone to do, meaning that essentially your model can have so many nonlinearities that every dot, here, let me go ahead and plot this again so you can see what I'm talking about. Just going to do this. Did I do that wrong? Oh, RH. Oops. So here we've been fitting a linear model, but you can imagine as you start stacking layers on top of each other, and then you add that nonlinearity, those nonlinear called activation functions. When you do that, you can actually just literally just fit a line that's so jagged that it kind of fits every single point here, and then your model has amazing predictive accuracy with respect to your data set. But if you gave it some new temperature or some new temperature and asked it to predict the relative humidity, it may not be able to get it because it's so concentrated. It's like memorized this particular data set. So I encourage you to go explore, grab one of these data sets. I had the link in the intro video for this for the U.S. Climate Reference Network. Grab that. Grab the daily data, grab the hourly data, see what you can find there. All right, enough of the pitch. No more pitches for how awesome this kind of data is. All right, so Keras, back to Keras. What can Keras do for us? Well, instead of writing this loop, we can replace this entire loop down here, this loop over the epochs, with a few statements and allow ourselves a lot more configurability that's not hard-coded as I've done here. All right, so let's go ahead and do that. Best way to do it, just go to the website. Google Keras, Keras Deep Learning. Scroll down. There's going to be some way to install it. Now let's see where the install is. I can show you guys. For those of you who use Pip, that's what I use. Do a Pip install. I'm going to show you how to do that real quick. Just come down in here, Pip install Keras. And I've also Pip installed a bunch of other packages. I've done numpy, pandas, matplotlib, seaborn. Oh, what other one did I do? Oh, TensorFlow, of course. So TensorFlow is the actual heart of Keras in this case. You can put other things behind it. That's not really important here, but just know that that's the true package. And I'll take a look at TensorFlow in a second to show you what that looks like too. But to install TensorFlow, it's a really cool machine learning package that was built by Google. And again, because Google is into the big data realm, they built their own package here. More about that later. Maybe in a later video I'll do something about TensorFlow. But TensorFlow here, I'm installing the GPU version. If you don't have a GPU, go ahead and just pip install this TensorFlow with the CPU. I installed the GPU version, so I did TensorFlow install GPU. All right, back to the Keras window. Here we go. And so I just stacked these all together. Pip install all these. I already have them installed. That's why it took a little bit. The TensorFlow library does take a second to install. Just be mindful of that when you jump in. All right, so now that we have it installed, what's nice again about Keras is they have really good documentation. So the way Keras works to build a model, and that's what we've done here is build a linear model, is you just have this thing called sequential. So I'll go ahead and copy and paste this section in here. Put it in my area. And what model does is say, I'm going to build a model now. This is a sequential model. What does it mean to be sequential? Well, I'm just going to start stacking layers together. So just like you would want to build something from the ground up, you say, I'm going to build a model. So you've made that decision. That's what this instantiation does in here. Next step is to add a layer to it. So now I want to add a layer. And it has many choices of layers. Keras does, and machine learning in general, or deep learning in general does. Dense layers are generally what you're going to use if you're doing something simple like this. So dense layers are just those nodes that are connected to other nodes without any other fancy information, like no temporal information, for example, is not included in there. That would be something like an LSTM, a long short-term memory. I think that's what it stands for, something like that. Look it up. It's in the documentation for Keras. So here we're going to grab a dense layer, and you can see they have, of course, a fancy dense layer configuration here for us. So grab that, put that in there. Oh, I already need to delete this model add business. All right, and we're actually doing, since we're only doing one layer here, and it's a linear activation, so nothing fancy, and only one unit. So what the unit is here, units, is how many circles do you want? How many nodes do you want? Here we only want one node, because what we're doing is a simple linear model. Activation, again, linear, because we're not doing any weird non-linearities. And then you have your input dimension here. So this is the size, how many variables are going in is what this is. Well, how many variables are we putting in? We're just putting in one, so our input dimension is 1. What I mean is, when you're looking at that node structure, how many input variables am I going in? I'm only using temperature in this case, one variable, to try to predict relative humidity. So the input dimension is 1. If, let's say, I use temperature and, incoming solar radiation, so how much sunlight's coming in. So I now have 2 variables. This would just change to a 2. All right, next, so now I've created my model here, instantiated it, added one dense layer. Awesome, let's do that. Next, what does the Keras website say? Oh, it says I have to compile the model. Okay, so once your model looks good, configure its learning process with compile. And you can see they have a handy little template here for us. Let's go ahead and grab that. And then describe what all this means. So here they have something called loss. Loss you can think of it in the framework that we had written below. Loss is how do I define how far off I was. So here I have in the way we had done it with just numpy, how far off were we is this error. And here we have a mean squared error. So we selected a mean square error loss. That's how we determine how far off we were from the actual answer. All right, so we can actually do that here too, because Keras has tons, well, I shouldn't say tons, it has a bunch of loss functions. And we can just type in mean square, I think it's squared error. All right, mean squared error. Optimizer, so this is how can I explain optimizer? Optimizer is this step in here. How are you going to define this update rule? So there's different ways that you can do it. For the purposes here, this SGD thing is called stochastic gradient descent. And just parsing that phrase alone can give you some insights to what's happening here. So gradients are what we have done, which is this change in error with respect to the slope. That is itself a gradient. So when you say the change in something over something else, that is a gradient. Stochastic means that it's going to be somewhat random. So it's not always going to take the exact same step that you're going to be taking. So stochasticity, when you think stochasticity or stochastic, think something random, some randomness. So we're going to be descending along the gradient in a slightly random way. All right, so that's stochastic gradient descent. We're going to keep that. And then metrics here, which is really handy. We put in accuracy, so we don't know how accurate we are. All right. So this compiles the model, loss, gave it an optimizer, told it I wanted accuracy. Sweet. What's next? Well, you can explicitly define your optimizer here. And actually, we're gonna do this because let me go and grab that, because we want to also define the learning rate. And you can see the learning rate is part of your optimizer. All right, so let's throw that in there. redundant. There we go. I don't know if I defined that. Yeah, I probably should have defined that up here. Models, Keras, optimizers, import, SGD. There's other ones, and another popular one, just to give you an idea, is Atom. A lot of people like to use Atom. So look those up. Again, those are all in the Keras documentation. Really cool stuff. Remove that. We're going to put in our learning rate in here. Boop. Nice. All right. We're getting somewhere. So now after you've done that, this just now defined the model, compiled the model, but now we actually have to run the model. So this is where the fit option comes in. Fit is the last little piece of the puzzle. Fit just means now, okay, go ahead and launch this loop. Go ahead and get this thing started. Let's see how it looks. So our input is the first one in here. That's X for us, or temperature, so T. But we gave it X because this is our normalized variable. So this is the one that we took and squished it down to have the mean of 0, standard deviation of 1. Perfect. And then what's our target? What are we trying to find? We're trying to find this real Y value. So this is our real relative humidity. We had defined an epochs above. Let's go back up there so we can take a look at it. All right, we defined epochs to be 50, learning rate to be 0.1, and we have these slopes and intercepts. We're actually not going to use these. We're not going to use these because Keras will take care of all of that instantiation for it. It will define an initial guess for slope, it will define an initial guess for intercept, and it will take care of that for us. The only thing missing here is batch size. I don't think I defined that anywhere. So we'll just say size in here, and we'll just define a size at the top. And the size is just the shape of X. For our purposes, we're just going to take the whole temperature structure, however many temperature data points we have, because we don't have a very large data set. If this were a larger data set, you might consider chopping this up into smaller batches. And the reason is if, let's say I had 1 million data points, or let's say I had 10 million data points. Well, my CPU may not be able to handle that many data points. So it may crash. I might get overflow in memory, and we don't want that. It's also going to make your computer really slow if you throw a lot at it at one time. So this is just a way of, although I have a lot of stuff in memory when I read in these variables, X and Y, I may not want to, when I'm doing the matrix operations in the background, when Keras is taking care of all that, you don't want to necessarily bog everything down. So this is a way to handle that. All right. There's other options in here to look at down the road that you might want to be aware of, and that's validation, split. I believe it's validation split. Look that up in the documentation, like I said. So this is just say, I want to split my data set up now. I want to hold some of my data aside, because I have so much, and I want to hold 20% of it. In this case, I put 0.2. That means I want to hold 20% of my data aside, and I want to calculate the accuracy given my model. So I'm going to use this. I'm going to calculate a model over here, train it, and then at every iteration, at every epoch, I'm going to check to see how good my model did against this held out 20%. That's what that would do. I'm not going to do it here because, again, I have such a small data set. All right. The other thing I want to do is I want to actually see my result like I did down below. So I'm going to grab, I think it's get weights, I think is what it is. Get weights. Something like that. And I think slope, let's try this. I think slope is, parameter, not weights. I think it's slope is like that. And intercept. So this is what, after my model gets fit, meaning it learns those parameters, I want to see what those parameters are. Dang, gummit. All right. I think this one's just parameter. Maybe it's 1? Maybe? Might just be 1, actually. We'll try that. I'll go ahead and print this. Slope, intercept. Let's exit here. All right, so just to recap what I've done here, back up to the top. So at the very top, loaded in numpy, pandas, whatever. First thing I did, load the data. Second thing I did, normalize the data, squish it down so that it goes from 0 to 1. That makes the learning faster, as you saw in the last video. retain my go back function here, so it'll allow me to change back from that squished down relative humidity back to the real 0 to 100% relative humidity. Define some constants, intercept. I don't need these, intercept and slope anymore. I'm going to keep them just for the sake of keeping them. Then you have learning rate, epochs. Below we have Keras part. Okay, we define model. Did I do that right? Yep. Yep. All right, good. Size of the data set, check. Said I want a model, go. Add a dense layer, single dense layer, linear. Input dimensions are 1. Compile the model. I want a loss function of mean squared error. I want this kind of optimizer, stochastic gradient descent with this learning rate. And go ahead and fit the model and then spit out my parameters. So this is almost exactly like this below, but as you'll see, we can add a few layers and see what happens. All right, let's run it. The moment that we've all been eagerly waiting for. Let's see what happens. Basic building blocks. Boom. Oh, I screwed up. What did I screw up about? Oh. Very nice. Let's just do that. It was a typo and something I didn't even care about. Let's try it. TensorFlow backend. Oh, did I not? Oh, I didn't define dense. Shame, shame, shame. I didn't do this import layer. See, this is what happens. You try to copy and paste from Keras and you screw up. You miss one import, and you embarrass yourself in public. It's terrible. All right, here we go. Oh, I finished. That was really fast. Oh, because I only said 50 epochs. So you can see how lightning fast that was. I went through 50 epochs, and just like our model with numpy went. Really quickly it converged onto our answer. So you can see it started out with a loss. Accuracy is bad, but we know it's bad. It's not, a line is not exactly the best thing to fit through this temperature relative humidity data set. In any case, we start out with a high loss, and it quickly dropped and sort of settled on this value of 0.95 after like 30 epochs. So really quickly it converged, and then it didn't really change. All right, we are left with a slope. Oh, I didn't do it right. That's good enough. Whatever. I'll just take that. Slope and intercept. These are our, these are our final guesses from the model. So let's see how it looks. Let's do it this way, actually. Let's just put it in here. So we're going to grab this plotting routine from before. Take that. Take that. Take that. I like that. All right. Stole that from before. This is our answer. Actually, can we just copy paste this? Let's give it a try. This might work. It will not work. Oh, that cleared the axes. All right, let's not clear the axis. Let's try it again. And there we go. See, the black line is what Keras came up with, and the blue line is what Seaborn calculates, not using a neural network, but using a more efficient algorithm for fitting a line. But yeah, that's pretty much it. Now you can add other layers. So if we wanted to come over here into the Keras model, we can just say model add, and we can add another dense layer over here. And we can say, I want 10 and activation ReLU, which is a rectified linear unit. It's another way to transform your data from being linear into something nonlinear. So it has linear unit in it. Don't be fooled. It's nonlinear. Okay. You can look up what that is, ReLU. It's very common and it's used a lot nowadays in machine learning. So let's just do that. Oh, I need to close off another bracket here. I want to see if I could get this thing working. Dense units. Let's put this at 10 as well. Just some random units. Activation equals linear. All right, so as I'm adding layers in here, you'll note that I did something. Let's make this non-linear too. There's some differences between what I had done. Nope. Things to note. Okay, before we wrap up, I've added a few layers in here. And you notice I don't have input dimension on these new layers. The reason why is because Keras is smart enough to infer what the size of the last layer was. It knows that the output of this one is going to be of a certain size, in this case 10, so it knows what it's accepting in this layer. Now, in general, that'll work for dense layers. In other more complicated layers, you might have to do some things like flatten it or reshape it a little bit. You can just follow along with the examples Keras has, and tons of people have other examples online that you can check out. The other thing to note, and I kind of glazed over this, is your output dimension. I have output units as 1. And this is the same reason why we had an input dimension of 1. We are going from temperature, a single variable, and we're trying to map that to another variable, relative humidity. So one variable is being transformed into another. That's why our dense layer here has to match the number of variables that we're trying to predict. In this case, the target variable. In our case, relative humidity. So let's say I was trying to take temperature, and from temperature I want to predict relative humidity and another variable like, I don't know, wind speed or something. That means I would have to change this to 2. And of course your target variable will change above as well. All right, let's try to run this and see if it fails, which it totally might. Actually never tried this before. This is good. It's like a live thing that I'm doing here. I never tried to do this yet. Let's see what happens. And something broke. That's good. Operand cannot be broadcast. Oh, crud. Why couldn't it be broadcast? This is what I mean about dimensions. So I clearly screwed up a dimension thing here. Shape 10. Oh, okay. All right. It did not work. How does I do this? This is debugging on the fly. I wonder what happens. I don't know. Ah, it worked. It worked, but it failed at the same time. All right, so it worked in that it compiled and ran, but we're getting a terrible answer here. This is a function of many things. I won't debug it here or try to diagnose it here, but hopefully you have the basic building blocks to go out and play around with Keras, and more importantly, hopefully you understand what's happening. If you want to see an extension of this, perhaps a more interesting model, maybe I'll do that next time around. Just let me know in the comments. Or if you want something explained a little bit in more detail, just let me know and I'd be happy to do it. But for now, go out and explore Keras and deep learning. I'll talk to you later.